Hi everyone, I hope you're having a fantastic jump dev in JuliaCon. My name is Mathieu Besançon. I'll be talking today about Scylla, which is a primal heuristic, so a primal algorithm for mixed integer optimization that is matrix and LP-free, which is exactly what that means. This is work with Suresh, Antonia, Ambrose, Alexander, and Johnny. We are all working at the TUS Institute in Berlin. We are, broadly speaking, working on computational, mixed integer, nonlinear, and or convex optimization, so on all of these various topics and different applications in energy or in machine learning, in transport and others. If you're interested, just feel free to reach out. All right, let me just slide myself up there and continue. So first, I'll give a brief introduction on mixed integer optimization, on why did we have some interest in this specific setting I'm talking about. And then we're going to see the Scylla algorithm and a quick or broad overview of the algorithm itself. And then we'll go over some of the key components of the algorithms that we saw before. And I'll conclude with some preliminary computational experiments. Right, so mixed integer linear, or broadly like mixed integer optimization, is a class of fairly hard optimization problems where you try to optimize a set of constraints with, here, for example, a linear constraints, and over a set of decision variables that have to take integer values, or at least a subset of your variables has to take integer values. So in that case, we'll take the simplest setting of this, so with this property, which is like the mixed integer linear optimization problem, which will be written like with a minimizing or maximizing a linear function subject to a finite set of linear constraints, variables belonging to some bounds, and some variables having to take these integer values. And we'll set ourselves a key constraint or key requirement here for algorithms we're trying to design, which is we'll try to find so-called LP-free algorithm. That is, we will try not to rely on the cheap accessibility or cheap availability of the solution of a linear relaxation of this problem. So a linear relaxation here would be taking the original problem and dropping the integrality requirements. This is much easier to solve. It's going to be solved in polynomial time compared to the mixed integer version of it. So we'll try to avoid requiring this. So we'll try to avoid having, like, assuming access to this LP oracle. Why? Well, basically, or one key element is that standard methods for LP solving, such as the simplex algorithm, which would be the central one, or the barrier or interpoint method, they both require matrix factorizations, either directly of a constraint matrix or of an extended matrix formed with the constraints. And this can be a high initial cost. This can be expensive for large-scale applications, and you might have to do it over and over when you change the constraint matrix. Furthermore, not all algorithms would require the exact LP solution that would typically be computed by these methods. So these methods will compute a solution to a very high accuracy of a linear problem. And we typically don't need that over time. We might need instead a bound, so a primal or dual bound on the LP relaxation, or we might want approximate primal values, so that is the approximate x that correspond to the relaxation, and so on and so forth. And finally, we'll try to leverage new possibilities for solving LPs. Right, so that was it. And the second thing I wanted to mention in this introduction was why do we care then about heuristics for a mixed integer optimization? Well, first, because again, this problem is hard, so you might not be able to solve it exactly. That's the first thing. And the key algorithm for solving mixed integer optimization exactly is the branch and bound or branch and cut algorithm, which also relies heavily on the availability of heuristics for computing feasible solutions. So even computing feasible solutions that have no guarantee can help drastically helps drastically your exact algorithms to prove the optimality of these solutions, or at least a bound on these solutions. Right, so we can now go on with the Scylla algorithm itself. So first, to give a quick overview of what's happening. So we take in a problem, so an initial optimization problem, say from a specified file or from JUMP or any other modeling language. We first pre-solve it using an out-of-the-box pre-solver called Papillo, which is also developed in-house at the Zuse Institute and used like in different in different solvers. We then apply a trivial heuristic, which is trying to fix variables at their bounds and propagating afterwards. And only after we run into the main loop of the algorithm, which would be first solving approximately an LP, so a linear relaxation of a problem or of a problem. We'll see exactly what that means later. And then either applying rounding to this solution from the LP, which will typically be fractional, or a so-called fix-and-propagate step. We'll see exactly what that means. If this is yielding an infeasible solution, then we can analyze the conflicts, that is, analyzing the contradictions between our fixings and some constraints that cannot be respected anymore. If this is feasible, then we have a primal value, so we won, we have what we wanted, but we can continue the algorithm by adding a cutoff constraint. So that is, we have an objective for our current solution, and then we can search the space of all solutions that are strictly better than our current one. And so we tighten the feasible set and we try to rerun the algorithm. And so either when we time out or when we reach something satisfactory or anything else, we terminate and then we post-solve. So that is, we take the pre-solving information, so that is the variables will reduce, the constraints will reduce, and we expand that back to a solution in the original space. All right, so to put this chart into pseudocode, so the algorithm takes the specification, a mixed integer problem with given data, and outputs either a solution or no solution. It also outputs additional information, which I'll talk about in detail a bit later. But the key thing primal heuristic is supposed to output is a feasible solution of a problem. Right. So the first thing we'll do is we will have a primal dual hybrid gradient PDSG loop here. And this one, so the inner loop there will try to find an approximate solution of a given linear relaxation with C hat here, which is originally our initial objective. Out of this, and it also takes as input like the previous primal solution if we have any. So we progressively improve our primal solution until a point where it's either LP optimal or approximately LP optimal with a certain tolerance, or our bounds are stalling. So that means the integer variables remain at the same bound for many iterations of the algorithms, or k reaches the iteration limit, in which case we just terminate on the budget. So the last case is not supposed to happen that often. We typically reach LP approximate optimality or the bounds are stalling. Then once we have this approximate linear relaxation solution, we pass this to a round fix and propagate procedure, which will either do, as we said before, a rounding stack on these fractional variables, or we'll try to fix these variables and propagate the fixings. We'll see also later what that means. Then, so we out of this, we get a solution that is hopefully MILP feasible. So it's feasible for both the linear constraints and the integrality constraints. If that's the case, then we greedily try to improve the solution by flipping the binary variables or the integer variables. So trying to improve locally by just switching a variable and then propagating accordingly. And once we have done this, so either we found a better solution or not, but in any case, we can apply a cutoff constraint. So that is, we try to find now solutions that are strictly better than our current one. And we repeat the process until we're satisfied. And so yeah, that's it. Otherwise, so the analyze part here is if we didn't find a MILP solution out of a round fix and propagate procedure, it means we have something infeasible, and in that case we have a conflict, and that conflict can be exploited to derive new constraints that are added to the problem, and that can make the future search process better. And then so we increment our outer iteration, and as a final step, we also modify our objective function to be a sum of the sum of the previous objective vector and a projection step or a projection part, or so in that case an L1 projection onto like projection onto the polytope of the previous integer point. Right. So we saw briefly the algorithm. I'll now go over the different components that we saw a bit quickly and that are worth paying attention to. So the first one is, we said that we didn't solve LP, but then in the algorithm I did solve an LP approximately. So what does that mean exactly? So in that case, I'm referring to the so-called primal dual hybrid gradient algorithm, also referred to as Chambolle-Park, which is a first order method for saddle point problems applied to the saddle point formulation. And in that case, this is a saddle point problem applied to the saddle point formulation of VLP. And the key implementation we're using here is from the paper Practical Large-Scale Linear Programming using PDHG from Propagate and others from 2022. So yeah, they are describing first how to apply specifically PDHG to linear problems, and then they describe a set of improvements that are specific to LPs. So or that are most likely specific to LPs, including restarts, adaptive step size, and also the effect of pre-solving, also using Papillo. The key, one important thing here is that it doesn't require, unlike the other algorithms, any factorization of a constraint matrix. It only requires matrix vector multiplications. So in that sense, PDHG or PDLP is a so-called matrix-free algorithm. So first, the primal step is, for both the primal and the dual steps, we have a gradient-like step, which will move towards feasibility of the equality constraints or of the linear constraints. And then we have a projection step onto the primal and then on the dual bounds. So that's the two steps we have. And then you have an adaptation of the two step sizes. Right, so that's it for, so I'll refer to PDLP for the specific implementation and for PDHG for the generic primal dual hybrid gradient algorithm. So yeah, the key thing, the two key things again are we don't require factorizations with this algorithm. The second is we approach the primal dual solution pair approximately and let's say slowly. So with this, we can know when to stop the algorithm, unlike simplex or barrier methods where you would either optimize fully or not optimize at all. But you don't really have this intermediate choice that we can exploit here. So we brought several modifications to the PDLP code to make it work for our use case. So the first one was warm starting. So we added the possibility of passing the previous primal dual state from the outer iteration of Scylla to the next one. So that way we warm started PDLP with a primal dual solution, since it doesn't specify anything on what the solution should look like. So what the initial pair XY should look like, and so we can just use what we think should be a good one. And the second thing is we use these custom stopping criteria. The first one being an adaptive error tolerance. So if we're early in the search process, we don't hope to find a solution too soon. And so in that case, we just use a very coarse error and then we refine it progressively. The second one being early termination. So not only when we are close to an LP solution and we're just like getting closer and closer, but also when our bounds are, so our integer bounds or the variables that are supposed to be integer remain at the same values for many iterations, because these are in the end the variables that we care about much. And once the integer variables are fixed, this is usually fairly trivial to compute the optimal value for the continuous variables. Right. So if you paid attention to it, the ideas taken here are fairly close to the so-called feasibility pump, which is another primal heuristic for mixed integer optimization, which alternates between solving an LP to project onto the polytope of linear constraints and rounding the solution to compute integer points that are not necessarily LP feasible. So basically you alternate between these two steps. So the rounding step is like a non-convex projection. So it's not given, this alternate projection is not guaranteed to work. In any case, it can cycle, for example. If it cycles, then you restart from a different starting point and you hope not to cycle again. And the objective adjusted feasibility pump also takes into account not only a projection, but also a projection and the original variable, the original objective. So it's a weighted sum of these two terms. So in Scylla first, we do this LP projection approximately with PDLP, that's what we saw before, and we replace the integer rounding with a fix and propagate procedure, which instead of just rounding to integer, will exploit the linear constraints to try to round in a smart way. So this was already suggested in prior work on feasibility pump, but we tried to exploit this here with a fix and propagate procedures that were very close to the one that were already in Papillo for pre-solving. So I mentioned fix and propagate several times now, just to give you a brief overview of what this means. So this is a set of techniques that are close to constraint programming, if you're familiar with it, and that consists in fixing a given fractional variable to a value, and then trying to deduce out of this fixing if other variables now are forced to certain values. So in that case, we have here an example of an LP feasible point with all fractional variables, and all of these three variables have to take integer values. So say you fix x2 to 0 now, so that means trivially that the second constraint now looks like x1 plus x3 have to be greater than 1. Okay, so it's saying at least one of the two has to be 1. But the first one is more interesting because it's now x1 plus x3 greater than 2. And so in that case, the two variables have to be equal to 2. And in that case, it means that fixing a single variable, if I propagate through my constraints, will make me deduce that my two other variables have to be fixed to 1. And so with just one single fixing, I can greatly reduce the number of variables of the problem for the next iterations. Right, so the fix and propagate part of the procedure takes like a given, so an initial fractional variable, and it takes also, so it takes the MILP specification, and it tries first to find a variable to round on and whether to round up or down. So this will be a selection step. Then we'll try to propagate the domain on using this round information. So this is the step we did on the previous slide. So I'm fixing x2 to 0, and then what is happening to the domain of all the other variables. So if my domain is empty, so this is to say that my problem is now infeasible, so I cannot have a solution, then I will try to backtrack. And we see here that we try to backtrack only once. We start with backtrack equals true, and then we, if we are empty, we try to round now. Instead of rounding at 0, for example, we round at 1. And so we do this while there are variables that are not fixed. So while some variables are uncertain, so we have not fixed them and we haven't deduced a value for them from the propagation. While this is true, then we select a new variable that is unfixed and we try to fix it to one of the two values, and we check if we are infeasible or not. Once this is done, we fix and propagate all the last unfixed variables, so the ones that we haven't deduced yet. If some variables are still free, then we can just fix them at their bounds. If the domain is empty, then, well, bad luck. This means that we didn't find a feasible solution in that case, so an LP feasible solution. But we could still round all the variables, and we tried to round them in a way that was respecting as much as possible the constraints. So that means that we have normally a good enough, a fairly high quality rounding or smarter rounding than with a naive integer rounding. Furthermore, so given the new domains, so the fixed domains of the variables, we can now run conflict analysis, which is a part that already exists in in all mixed integer solvers, and that will try to deduce out of the current fixings what is a constraint that is currently not respected and that should be respected for my problem to be feasible. And so this set of conflict can then be leveraged on the next round, and for example to reduce the domain of variables and so on. And so I return my integer point that is not LP feasible, my conflicts. Otherwise, if I found a smart feasible solution, if I found a feasible solution, I greedily try to optimize it over, so to optimize like one variable only, so flip one of the binary variables to improve the objective, and then return the feasible solution itself and an empty set of conflicts. All right, so we run the fix and propagate part and the conflict part in parallel, and we try to assess how many times a given technique was finding the better solution. So this is the number of solutions found over several runs, and we saw which ones were finding interesting solution. So in that case, aggressive one-up is, so we run a one-up version where at every time we try to flip the sign, we also run fix and propagate to take that into account for the other variables, to be sure to have like the most feasible possible one-up that we can. So this was definitely finding way more solutions. And then forecast, so these are different diving strategies that we can use. And so some of them were more successful than others. Forecast diving, for example, was a fairly successful one. Right, as a last part, I wanted to go over some preliminary computational experiments we had. This is still fairly limited, and we are currently working on a prototype of Scylla, or this was like a prototype version, which is way less optimized than the state of the art we compare ourselves against. So we use instances from the MILP 2017, which is a fairly standard set of instances that you can categorize by difficulty, by numeric stability, by whether somebody found a solution already or not, and so on. And we use a set of instances that is identical to the feasibility pump 2.0 and later work by JuliaCon and others. So the C++ implementation of a modern feasibility pump is more or less state of the art and corresponds to improvements over the feasibility pump 2.0 and others. That is taking into account, for example, the specialization of the propagation or fix and propagate step on the type of constraints. So in our case, for Scylla, we considered only a generic MILP. This feasibility pump is fix and propagating using the constraint type, for example, set covering or knapsack constraints and so on. The other noteworthy difference is that the feasibility pump by default or by nature will always terminate when a feasible solution is found, and so we can only compare the runtime with time to first of Scylla. Right, so this is the time to first performance profile. So Scylla is definitely doing much worse in terms of gap and time on the first. That's because the first solution found by Scylla will quite often be the trivial heuristic or a simple rounding. And in that case, the solution will not be as good as something that is fixed and propagated in a specialized way. And on time, we are paying the cost of having several pre-steps before, and also a bit of overhead from the Julia prototype compared to something that is compiled straight away. So yeah, this was like run every time in a single bash command, so we did have a bit of overhead. So yeah, now in time to best, where Scylla is run for 10 minutes, well, both are run with a timeout of 10 minutes. We are fairly competitive, or we are comparable in terms of gap. So in terms of performance gap, the two are really playing in the same court. So that is, we find solution qualities that are comparable, especially for harder instances. We are getting better here compared to the easiest one. So we do find a gap that is fairly similar. In terms of time, again, so this is not really comparable here because Scylla will be running basically until it times out, while the feasibility pump will be running until it finds the first solution. So the key thing is, if we run in time to best, we have, in some cases, better solutions. Looking at so to analyze a bit more the results here, first order LP.gel is a prototype from the Applegate and others paper. This was still two proof of concept for having a robust implementation. For example, on some hidden industrial problem sets, it wrongly detected feasibility or unboundedness of some problems. So our takeaway was that it should not, we should work a bit more before incorporating this into a solver. And Google Research has now released a more stable version of PDLP, which is now in OR tools, that we are using for a second version of Scylla. The other thing we noticed on some instances, so of course I cherry-picked here 2 of them, but there are way more that are representative. Scylla is more interesting on much harder instances than the feasibility pump. So to give you an impression here on these two, so a single LP solve for these 2 instances was 70 and 270 seconds, which is fairly significant. In 10 minutes, so there was no solution found by feasibility pump, and Scylla found a feasible solution within 30 and 60 seconds. So in less time than it takes to solve a linear relaxation of a problem, which is, to remind you, much easier, we found an integer feasible solution, and then we can improve upon it afterwards with the algorithm. All right, as key takeaways, so first, this is a fairly novel primal heuristic that exploits new techniques for solving LPs that are fully matrix-free. So we only require sparse matrix times vector multiplication, no simplex run, no interpoint whatsoever. And in addition to primal solutions, it provides useful information like conflicts, so all the conflicts are valid. It also provides a primal and a dual bound. Since you're running a linear relaxation of your problem initially, you do have a dual bound on your problem. And I think so this algorithm can be especially interesting where other heuristics would struggle. For example, all the heuristics like feasibility pump that assume an LP oracle is available and fairly cheap. All right, and in open perspective, so again, we're trying to build a better version using, or a 2.0 version using OR tools, the OR tools version of PDLP, which is more stable. We're thinking about incorporating the conflicts not only in the fix and propagate part, but also in the LP relaxation solved by PDLP, and parallelizing and making things asynchronous. All right, that's it for me. Thank you, and see you at JuliaCon.